Okay, so you have derived a whole bunch of unblocked algorithms, you've derived a whole bunch of blocked algorithms, and now you may ask yourself, which algorithm should I pick when? Well, let's first start discussing blocked versus unblocked. Well, obviously, when you do a blocked algorithm, at some point you have the LU factorization of the current block on the diagonal that needs to be performed. You could use a blocked algorithm with a smaller block size for that, but at some point you need to switch to an unblocked algorithm. That's not unlike the matrix-matrix multiply that was discussed in the enrichment for week 5, where at some point at the bottom of the food chain there was a rank 1 update based algorithm that updated the tiny little matrix that was sitting in the registers. So the same kind of thing would happen here as well. Okay, well, let's focus a little bit on blocked algorithms then. Which invariant or variant should you use? Obviously, when you derive the algorithm, you start with an invariant. So you may think in terms of the algorithm associated with the invariant. Most people really only look at the algorithm that comes out and would then discuss the variant instead. Alright, so over here I have made a picture that depicts a matrix, and let's assume that we've gotten through the matrix up to a certain point so that we can discuss what is in the different quadrants and therefore discuss what might be the benefits of the different algorithms. Alright, well, let's think for a second about the algorithm where only the top left is done, but the rest of the matrix is left completely alone. That's sometimes called the bordered algorithm in the literature. We call it variant 1, which corresponds to loop invariant 1. Alright, well, let's contemplate this. What if you expect for there to eventually be a 0 on the diagonal, and that therefore you are using this algorithm in part to detect that the matrix has a problem? Once you end up encountering a 0 on the diagonal, you'll end up doing a divide by 0, and that's a problem. Okay? Notice that this particular variant will have performed the least computation leading up to the point where you find out that there is a problem. So if the purpose of the game is to detect that there's a problem, then you may actually want to use this particular loop invariant. Okay? Now, so that's would be variant 1. Let's go to the other extreme. What we discussed in the enrichment for week 5 was that inherently a high-performance matrix-matrix multiply itself is cast in terms of matrix-matrix multiplies. And the particular shape that's important along the way is a rank 1 update, which is a tall skinny matrix times a skinny long matrix, or whatever you want to call it, a column panel times a row panel. Now, variant 5 maintains the loop invariant where this, and this is completely done, and this quadrant is partially updated, and as a result the blocked algorithm casts most computation in terms of exactly that shape of matrix-matrix multiply. Okay, so now what other algorithms are there along the way? Well, let's look at one more. We don't need to do this exhaustively. Recall that variant, I think it's variant 3. Anyway, it's the loop invariant where this is done, that is done, and these blocks of the matrix have been left alone. It's either variant 2 or variant 3, I forget. That particular loop invariant has a very nice property. Everything to the left of this point has finished. Everything to the right of this point has been left alone. Now, when you try to solve extremely large problems, problems so large that they don't fit in your memory, you have to store them on disk, you run the risk that during the computation your system fails.
Now the good news is the data involved in your computation is sitting on disk and therefore should be okay. The bad news is if something happens in the middle of updating a further panel of the matrix, then you may have a partially corrupt matrix and you won't know what to do. Now to overcome that, what people do is something called checkpointing. They sort of say, well, up to a certain point everything has been properly updated on disk. I'm going to do a small sliver of computation. Once that computation is done, I'm going to very carefully update the data on disk so that I know whether it actually was updated correctly. And at that point, I move the checkpoint forward to the new point. Okay. Now, notice that actually variants 1, 2, 3, and 4 have the inherent property that you update a relatively small sliver of the matrix, and therefore they inherently lend themselves to checkpointing. The reason why this particular algorithm is nice is that when you store data on disk, you again tend to store it by columns. Reading from a disk is much more efficient when you do one huge read as opposed to little pieces. So when you come to a new piece of the matrix, you can read that all in from disk as one big chunk of data. That makes the reading from the disk very efficient. Then you can do computation with it where you read pieces of the matrix to its left. And then eventually you can write that out as one big chunk of data that gets written. And then you can move the checkpoint forward. Okay. By the way, that particular algorithm is sometimes called the left-looking algorithm. It's left-looking by virtue of the fact that most of the computation comes from data to the left of the current panel of columns with which you're computing, which is a little forced, perhaps. Okay, so what have we seen? We've seen a bordered algorithm, we've seen a left-looking algorithm, we've seen this algorithm variant 5, which is sometimes called the right-looking algorithm, and what we have argued is that each of them has merit under different circumstances. And therefore it's great to be able to systematically derive all possible loop invariants and all possible algorithmic variants from those loop invariants, because then you can reason through which algorithm might actually be most appropriate for a particular circumstance.